General Chemistry 2 is essentially the study of chemical reactions. In the study of chemical reactions, there are three big picture topics that we will cover. These include chemical kinetics, chemical equilibrium, and chemical thermodynamics. Chemical kinetics is the study of rates of reaction. Chemical equilibrium is essentially extent of reaction. And thermodynamics is the feasibility of a reaction. Real quick, here we have a little graphic to illustrate how these tie together. And in general, here's a reaction, as you are familiar. Reactants go to products, R for reactant, P for products. And this is concentration changes as a function of time. Now, in the beginning of a reaction, before the reaction starts, there are zero products, right? And there's 100% reactant. So we will start that right here at 100% reactants. And products are 0%, starting right here. Now, I want you to think of the reaction like horses in a gate, a horse race. And in the condition now, it is before the race starts. The gate has not opened yet. Now, open the gates and let the horses run. It is open the gates and let the reaction. Well, what happens to the concentration of reactants logically, and what happens to the concentration of products logically? Well, the reactants are going to go down because the products are going to be made out of the reactants. So we'll see a trend that will be of this generic type. And proceed like that. Whereas the products being formed from the reactants will increase in concentration over time and will form a trend like this. Now, using brackets in here, and you'll see that many, many times in the near future, refers to molar concentrations. And we'll elaborate on that when we get deeper into solutions. Yeah. Divided into two parts to right here, and then petition from here to that petition, and then we'll talk about this one. This first region is called the kinetics region, whereas this second portion, I'll move that over some for neatness. Whereas this portion where the slopes go to zero are equilibrium region. as you can see here. Well, the principles that govern these and the study of kinetics, or so rates of reaction, are based upon the fact that anywhere along this curve, as the products are generated or the reactants are consumed, there is no constant slope. So as we can place a ruler there and draw a line against any one point in here, and as we get closer to the equilibrium point, the slope is constantly changing. So as long as that slope is constantly changing, we're in the kinetic region, which deals with rate of reaction. And rate is a speed. It's like miles per hour, but in chemistry it's concentration over time. So it's a change in concentration over change in time. So our analyses that will take place are dealing with reactions and solutions that we have to know about concentration factors and divided by time to give us a rate of reaction. And each type of reaction has its own personal rate as it proceeds from start to the equilibrium point. Now the distance technically between zero and the equilibrium point is called extent of reaction. Extent of reaction point. And the extent of reaction point is the point at which the equilibrium principles take over. That's where you see visibly the slope of the concentration curves become zero or do not appear to change any longer. So what it's telling you also is that the rate of reaction going forward is the same as the rate in reverse. Now, it's called a dynamic equilibrium, and that's the law of mass action. That's the fundamental principles that we will use to study the concepts of reactions while in equilibrium condition. In reverse. So we will show you how to deal with that and apply that into what we call an equilibrium constant. And it is a characteristic of a reaction. Equilibrium constants and rates of reactions are like fingerprints of reactions under certain conditions. So it's very important that you characterize a reaction, rate of reaction, by its change in concentration over time, or if it's in an equilibrium condition, what is its equilibrium constant, a number that reflects the size of this extent of reaction. And essentially, equilibrium is the extent of reaction. It is a point beyond which the concentrations remain constant. Well, thermodynamics is a very young science, and the feasibility factors mean simply that will the reaction work or will the reaction not work? That's all that essentially means. So thermo is the purpose of thermodynamics is to determine feasibility. I'll move that down. Will it work or will it not work? Well, there's a blend of concepts in both kinetics as well as in equilibrium that lead us to what we call thermodynamic properties. So it is the thermodynamic properties that ultimately leads us to, yeah, the reaction will work, or no, it won't work. And so this is kind of a thumbnail of where we're going in the big picture. All of these three subjects depend very, very much on your understanding the stoichiometry of chemical reactions and how the stoichiometry of reactions occurs and is dealt with in solution phase. And so just about every problem you'll work will have a solution phase concept embedded in that problem, where you'll have so much solute and so much of a solvent to produce so much of a reacting product. Anyway, so we want to look now at stoichiometry. Of chemical reactions. In your handout, you will have a little table that will look like this. And it talks about what can be calculated from a chemical reaction. I showed you a little bit of that from the first lecture that I did on this this week. So the question of today is what can be calculated from equation or reaction. Okay. Well, I'm going to use the synthesis of ammonia equation. Oswald process ammonia is 3H2 as a gas plus N2, one as a gas, goes to 2NH3 as a gas. Okay. Now first, we want to make a list of those items that can be made or calculated from a chemical equation. Just kind of partition everything off like this and then fill in the blanks. Like this. Well, the first thing from a chemical equation, we can calculate moles. What's a mole? It's the mass of substance containing one Avogadro's number of particles. So that can be a formula weight. One mole weight is the quantity of sample. It's a mass number that contains one Avogadro's number of particles. The coefficients of the balanced equation are moles. So we have 3 moles, 1 mole, and 2 moles. Now, the coefficients in this equation have been reduced to the smallest whole number ratio. When that case exists, then that equation, as written in the molecular form, is called the standard equation. So you see the coefficients are in the smallest whole number ratio in that. Now I can divide by 2, multiply by 2, or whatever number, and the equation's still valid. You just have to do it all the way through the equation on both sides of the arrow. And I could double this, goes 6, 2, and 4. It's still a valid production equation. It's just not in standard form if you do that. But you can scale it up or scale it down relative to the mole values. So, and another thing in here about moles is we have a reaction ratio. It always reacts in a 3-to-1 ratio between hydrogen and nitrogen to produce 2 moles of ammonia. And it doesn't matter if you have 20 moles of hydrogen, it only uses 1 mole of nitrogen if that's all you have. So it always reacts in those quantities. And 3 moles of hydrogen, no matter how much nitrogen you have, will produce only 2 moles of the ammonia. And those are called reaction ratios. Reading the equation is one way to look at it. So in reading the equation, you want to certainly be aware of reaction ratios. And we'll use that extensively here in a few minutes to illustrate some stoichiometry. Well, that's the first thing you can calculate from a chemical equation, and we'll work some problems on that. Another thing is mass values. And we call this equation mass. So the 1 mole of a substance is 1 formula weight. So when we look at the formula weight of hydrogen, molecular hydrogen, its value is 2 grams per mole. 1 and 1 is 2. Okay? But in the equation, we have 3 moles. So that's 6 grams. So we have 3 moles times 2 grams per mole, and that gives us 6 grams equation weight from the standard equation. Here is 1 mole, of course, is understood, as you well know, to be 1 mole of molecular nitrogen. So 1 mole, and 14 and 14 is 28 grams per mole. And so the equation weight for the nitrogen, molecular nitrogen, is 28 grams, 1 times 28. The equation weight for ammonia, 1 mole, is 14 and 3, 17, and so that is 2 moles times 17 grams per mole, 34 grams equation weight. So that's the second thing that can be derived out of an equation as far as the numerical values. And you can scale those up or down proportionally, and they will scale relative to each other. Now primarily I'll tell you to work off of moles, and you'll see why shortly. Another thing you can calculate are particle numbers. And that's typically in relationship to Avogadro's number, and we use a symbol N-aught, N subscript aught, where Avogadro's number, as you know, is 6.02 times 10 to the 23rd units of whatever you're studying. In this case, molecules or atoms. Now these are all molecules: molecular hydrogen, molecular nitrogen, molecular ammonium. So here we're talking about 3 Avogadro's numbers of molecular hydrogen, 1 Avogadro's number of molecular nitrogen, and 2 Avogadro's numbers of molecular ammonia. So if we wanted to know the absolute number of molecules of molecular hydrogen, it'd be 3 Avogadro's number of hydrogen. The number of molecules of nitrogen would be 1 Avogadro's number of nitrogen, and 2 Avogadro's numbers of ammonia. And like that. So those are the first 3 things you can derive right out of the standard equation itself. Again, you scale those up and down. We'll show you that shortly. Now, the next thing that can be determined out of the equation is gas volumes. Now, the standard equation, as written, is understood to be at 0 degrees Celsius and 1 atmosphere. Those are standard gas law values. as you may recall from studying gas laws, Charles' law, Boyle's law, Gay-Lussac, and so forth, like that. So when we talk about an equation that contains gas phase components like 3 moles of molecular hydrogen in gas form, we call them molar volumes, VMs. And I'll move this up now to give us a little more room under here. A VM is, by definition, a molar volume. And is, by definition, 3 stripes is a definition, the volume occupied by 1 mole of any gas. Doesn't matter what it is. SO2, H2, N2, argon, 1 mole weight, 1 formula weight, doesn't matter what gas, is said to occupy 1 molar volume. They all do the same thing. Now, it is important to understand that a molar volume being the volume occupied by 1 mole of gas, you can't assign a number to that in the way I've just described it, unless you apply the temperature pressure conditions to the situation. So the molar volume must be specified at a given set of conditions, and is typically under standard conditions called STP, that is at 0 degrees Celsius and 1 atmosphere pressure. Then 1 VM can be defined as 22.4 liters for 1 mole of any gas. So 1 mole of any gas will occupy 22.4 liters, but you must specify the conditions. If the temperature is higher, you will have a bigger volume. If the temperature is below 0 degrees, you'll have a smaller volume. So it is very important that you understand that the gas volumes to be specified, you have to specify a temperature pressure. Now, having said that, and also identifying the written equation as I've given you, the molecular equation balanced in the lowest whole number ratio, like I've shown you, is the standard equation, is assumed to be at 0 degrees and 1 atmosphere. You don't have to be told. You won't have a sidebar that says this is its standard conditions. So if you see a molecular equation, it's got a gas phase component in it, and it has a 3 in front of it, that's 3 molar volumes, and you can legally multiply by 22.4. But if it says it's 25 degrees, you can't do that, because it's not a 22.4 number. It's something like 24.5 or something like that. It's larger. So when you look at this equation here, we're looking at 3 molar volumes. Now, under standard conditions, yeah, that would be 3 times 22.4. 1 molar volume, well, let me put the H2 in here. This is 1 molar volume of molecular nitrogen and 2 VM of molecular ammonia. And VM equals 22.4 if we're at 0 degrees and 1 atmosphere. If not, again, it is has to be adjusted. Please correct it right here. Just a typo. I should have put 2 molar volumes in there. Mistake. Okay. Let's see where we are on this. Okay, the next thing is associated with chemical equations or energy values, and there are 2 kinds of energy considerations that you are probably familiar with: endothermic, exothermic. Actually, there are 3. Isothermic, it means no change in energy in the process, but we'll just work with the first 2. So that leads us to what we call thermochemical equations. So when we deal with chemical equations, and energy values. We refer to them as thermochemical equations. And you have formats for exothermic and you have formats for endothermic. Let's start with the exothermic format. Or reactions. Now, the ammonia reaction is an exothermic reaction, and there are two ways to write the thermochemical equation. Separate the energy number from the equation, that's one way, or incorporate the number into the equation is the second way. So the first way is, say, 3H2 gas plus 1, I'm not going to put 1, N2 gas goes to 2 NH3 gas, semicolon, and this is called an enthalpy number, heat of reaction. Now I'll put that down here, delta H. Or heat of reaction is what it's referred to, an enthalpy number. Now, it's an energy number, and when we get to thermodynamics or thermochemistry deeper into the course, we will explain why the symbology is as it is. But right now, just accept the fact that H, capital H, is a heat of reaction. And in this reaction is a minus 91.8 kilojoules for that heat of reaction. And what it means is 3 moles of hydrogen reacting with 1 mole of nitrogen to produce 2 moles of ammonia always gives off, because the negative number indicates exothermic, from the reaction loses 91.8 kilojoules. Now, a second way to write this is to incorporate the number in the body of the equation. And to illustrate it as an exothermic, we take the number and put it on the product side. You don't put negatives into the body of the equation. It's written like this: 3H2 gas plus N2 gas goes to 2NH3 gas, and then because it is an exothermic, the energy number is placed on the product side. And you'll see in the next illustration, if it's endothermic, the energy number is placed on the reactant side as an absorbed energy. So in both of these, the energy numbers indicate exothermic. Now, both of these formats are used on exams and in your literature and in textbooks, so to your advantage to be familiar with this. It means the same thing, except it's an exothermic in that the number is on the product side. Moving on to the format for endothermics, to get it out of the way. We'll take the evaporation of water. That's pretty straightforward. The first format is to separate the energy number from the equation. And here's a simple equation going from liquid to the gas vapor phase, semicolon, and delta H of reaction, enthalpy of reaction, is equal to 44 kilojoules. So it takes 44 kilojoules to evaporate 1 mole of water from the liquid form into the gas form. Well, if you incorporate that into the equation, the appropriate format is to put the energy number on the reactant side, like this. H2O as a liquid plus 44 kilojoules, meaning that it's absorbing the energy, going to H2O as a gas. So it's to your advantage to become familiar with the symbology and the formats that are used for the two methods. Well, they are, the molar amounts are always proportional to the numerical value of the energy number. If I have 3 moles of hydrogen, I'm reacting with an excess, if you would, of nitrogen. Excess means I got more than I need. I'm only going to use 1 mole. I will always get 91.8 kilojoules exothermic. And then if I evaporate 1 mole of liquid water, I will always require an input of 44 kilojoules. So if I doubled that, it would double the energy number. If I doubled the hydrogen with an excess of nitrogen, I would have to double the energy number. So I'm trying to orient you with how the standard equation is written in symbol form and is manipulated in some of the examples. Now, we need to work some problems around this, and the essence of the problems that I want to work is using the mole concept to solve chemical reaction problems. You'll hear me say, convert the data to moles, solve by ratio or ratio inspection, and then if they want something else at the end of it, then you convert back. Well, the second table in this list is a list of how to calculate or convert data into mole values and then use them into the equation. And you'll understand when I start using some examples here. If you're given grams, how do you get to moles? You always divide by formula weight. Grams divided by formula weight. In other words, how many formula weights are there in a given a mass? Okay, does that make sense? Okay, or if you have particle numbers, how many moles do you have if you're given a whole lot of something in terms of Avogadro's number like data? You divide by Avogadro's number because 1 mole is an Avogadro's number. If you are looking about gas volumes, you assume the equation is at standard conditions, then you take whatever gas volume you have, if at standard conditions, and divide by 22.4 because that is the volume of 1 mole light. So, and then on energy values, 1 mole will have, it'll say kilojoules per mole. You divide that kilojoule number into whatever mole number you got, mass number you have, and get your energy, the number of moles anyway. We'll show you. Now this one is the one that is so important to you. Molarity and volume data. This is a concentration term with a volume term. Data will come to you in what we call solution data. That's a volume and a concentration together, matched together within a problem. Okay, let me show you this. There is a topic called volumetric analysis in Chem 1 that now, what I'm showing you is solution data. So here you see 44.8 milliliters of a 0.150 molar sodium carbonate solution. Okay, that's solution data. And you've got a reaction down here that reacts with nitric acid 2-to-1. Well, you need to take those numbers and convert it into moles. So if you know the moles of this one, it takes twice as much nitric acid in the reaction with whatever you have. Now, how do you take that kind of data? If you see those two numbers together, a concentration term and a volume term, what do you do with it? you multiply molarity times volume, but the volume has to be in liters. That will give you the moles of solute in solution. And we'll emphasize this again here in a few minutes and work a number of problems that deal with that. So just to show you, and you can see this in other problems down here, it gives you milliliters. Here's one, 49 milliliters of 0.15 molar calcium hydroxide, whatever the problem deals with. But when you see that combination, you need to be able to convert to moles to work a chemical stoichiometry problem, especially when it deals with solutions. So that's why I use this section right here. I'm sorry, let me move that over just a little bit, to say how do you convert solution data to moles? Molarity times volume in liters will give you moles. And over here I give you an example, giving you 25 milliliters of 0.123 molar sodium bromide. I multiply 0.025 times 0.123 and I get 0.0031. That's the moles of sodium bromide. So all of this table down here are different ways to take data and convert to moles. Now, it may not make any sense to you right at this point, but after I work a few problems and work through each one of these, hopefully it will be a more visible technique to you, and you'll understand more about how to deal with this in terms of those types of data. Everybody get one of these? Okay. Okay, stoichiometry. Reactions problems. As you've gone through your courses in the past, many of you have learned certain ways to deal with these. I'm going to show you my way of dealing with these, and it's just one of several. Now, I don't care how you work the problems because there's going to be a multiple choice exam anyway. And but this I find is the most direct, using the mole concept, dimensional analysis, however you want to do it. Okay, it says here, given the equation, lithium hydroxide plus hydrobromic acid going to lithium bromide and water. In this, it says if you start with 10 grams of lithium hydroxide, and how many grams of lithium bromide will be produced? And in this context, you assume excess hydrobromic acid, and water is irrelevant in this particular problem. Now, the essence that I'm trying to teach you is convert to moles. And once you get to moles, you can compare the mole values to the coefficient values and see how the mole number will change, and like this. So lithium hydroxide, we need to divide by the formula weight of lithium hydroxide. Of course, lithium is 7/1624 grams per mole. It's just lithium is 7 grams, oxygen 16, and 1 gives us 24 grams. 24 grams per mole. And so, let me find that later. So that's a 0.42 mole lithium hydroxide out of the given data. Well, when you look at the equation and compare the coefficients of the standard equation between lithium hydroxide and lithium bromide, what do you see? It's a 1-to-1 reaction ratio. So the moles of lithium hydroxide equal the moles of lithium bromide produced. So if we are using 0.1 1 mole lithium hydroxide, it's going to produce 1 mole, but if we're using 0.42 mole lithium hydroxide, this is going to produce the same number in mole value, 2 mole of lithium bromide. Then you convert it back to grams, is what they're asking. You simply multiply that by the formula weight to get the total grams of the lithium bromide out of this. So the lithium, again, is 7 plus bromide, 80. Yeah, 80. So that's 87. So that's grams lithium bromide would be 0.42 mole times 80 grams per mole. Moles drop out. Times 87, excuse me, 87, not 80. 87. And 36.3 is what I get. 36.3 grams lithium bromide out of that. So convert to moles and compare the ratio, and then convert to whatever you need after that. Okay, we're given C2H4 ethylene is C2H4 plus 3 moles of oxygen goes to 2 moles of CO2 plus 2 H2O. Okay, in this we're given 45 grams of ethylene. How many grams of carbon dioxide will be produced? Well, we need to convert to moles by dividing by the formula weight. This is 28, 12 and 12 is 24, 5, 6, 7, 28 grams per mole. .61 mole of the ethylene is used. Okay, when we compare the coefficients, it's 1 to 2. So the CO2 mole-wise will be twice whatever we use in the ethylene. So the yield will be 2 times 1.61 mole in terms of CO2. Like that. And now if we want to get to grams, we multiply by the formula weight of CO2, 16, 32, 44 grams per mole. 16 16 is 32 plus 12 is 44, like that. And I get 141 points, and probably rounds to 2 sig figs 140 or something of that nature. So what I'm hoping you're starting to see is if you can get the data to moles, you just look at the equation and you can get the moles of yield or moles of reactant that they're asking for. And then at the end, once you get that, then convert it to whatever you need. Okay. This third one in here is magnesium plus 2 moles of sodium fluoride goes to magnesium fluoride and a couple of sodiums. If you start with 5.5 grams of sodium fluoride, how many grams of magnesium fluoride will be produced? Same kind of problem. And grams, convert to moles and see what the relationship is. So looking at it, it's going to, whatever you get and convert this to moles, it's going to divide by 2 will be the moles here, and multiply by grams at the end of it. Hopefully you're starting to see that pattern. So fluoride's 19 and 23. That's 42. So we want to divide this by 42 grams per mole. That's 0.131 mole of the NaF. And so the yield of the magnesium fluoride, when we compare coefficient, will be half of what we had for the sodium fluoride, so it'd be 1/2 of the 0.131 mole. Zero point 0.065 mole of the magnesium fluoride. And then times the formula weight of the magnesium fluoride. 62 grams per mole for the magnesium fluoride. 19, 19, and 24 is what I did. It's 62. And I get 4.03.
82.
Grams of the mag. Well, it rounds up. Depends on how accurate you are with your atomic weights and when you calculate moles. I'm just rounding everything up for right now. Pretty much the same idea. 2HCl plus the sodium carbonate goes to 2 NaCl's. And make it look like an NaCl. Plus hydrochloric. So 4. If you start with 20 grams of hydrochloric acid, how many grams of sulfuric acid will be produced? Same idea. And that's a 2-to-1, so whatever moles you generate, you divide by 2 and then times the formula weight. And then they've got 30 grams rounded to, well, let's see, 36 grams per mole for hydrochloric acid. So that's 20 over 36 and then moles. That's 0.56 mole HCl, and so that will give you 1/2 of the 0.56 mole of the H2SO4 right there. And then it will be 0.278 mole. And that's 98 grams per mole. I just happen to know that one. And that's 27.2 grams absolute. Here's a case where you only have one sig fig in the data. So this would round to 30 grams. That's where they get that. So to reinforce the question you had earlier. Okay, you'll need to grab this sheet again if you've got it available, because we'll do a reference on that here in a minute to show you how these are dealt with. Now, given 25 grams of magnesium and 50 milliliters of the 0.15 molar hydrochloric acid solution, what volume of molecular hydrogen will be generated at 25 degrees Celsius and 735 millimeters of mercury? That looks like a lot of mess, but it's not. If you translate this problem into moles, it will not be that difficult, in my humble opinion. First thing is convert all the data to moles. Well, we've already seen how to convert grams to moles. We divide by formula weight, and from the periodic table, that's 24 grams per mole. That's why I have to. 24.3 grams per mole if you want. So we get the moles of this one real quickly. And that gives us 1.03 magnesium. And so that's going to react with hydrochloric acid. Now, what did I say about this? This is a combination of a volume and concentration number in the data stream that you have in the problem. And to calculate moles from that, look at the bottom of that sheet down here. It says molarity to molarity and volume data. Moles is equal to molarity times volume expressed in liters. And I'll give you an example over here. Well, in this particular one, it would be volume in liters would be 0.05 liters, because you divide by 1,000 times 0.15, and the product of those two gives you moles of the HCl that you're reacting in here. Molarity times volume in liters. Please kind of get that into your mind, because those two always come together. They are moles. And so this would be 0.0075 mole of HCl. So when we look at this between HCl and magnesium, okay, we're not going to use all the magnesium, and so the limiting reagent is the smaller of the two mole numbers. Now we can divide. Now there's a quick way to determine limiting reagent in a series like this. Convert everything to moles and divide by the respective coefficient. The smaller number is always the limiting reagent. Convert everything to moles, divide by the coefficient. And if we divide by the coefficient, 1, divide that. Well, you can tell if you divide by 2, that's still going to be smaller than this one. So this is the limiting reagent. But what does that mean? It means that's the component of the reaction that when it disappears, the reaction will stop. And anything else in the reactant side will be in excess. So we will have a large amount of magnesium in excess. We will only use it's a 2 to 1, half of 0.0075 mole magnesium. That's all we're going to use. And subtract that off of the 1.03, right? If you just reduce it, that's all you're going to use, because that's how much you have to work with. And so the reaction will stop. Why will it stop? Well, there's no more hydrochloric. It's all been converted over to magnesium chloride and hydrogen gas. All right, now next thing is, well, how many moles of hydrogen gas will be produced? Well, we see here in this is 2 moles, is 2 to 1 is the reaction ratio. So if I have 0.0075 mole of hydrochloric acid, the yield of H2 for this will be half of whatever the moles are for HCl. Well, I need 1/2 of 0.0075 mole of H2 will be the yield. And so, whatever that half is. 0038. I know it's getting kind of mixed up there. But look at what the simplicity of this is. I converted everything to moles and then compared to the limiting reagent. That's all I did. And the limiting reagent determines how much yield you'll have on the product side. And so we only have 0.0038 mole because in the reaction it's a two parts HCl to yield 1 part H2. And as a result, I would need to cut the HCl mole number in half to get the moles of H2 in the yield. Everybody okay? See what I did here? Now, what is that volume? If you take that number times 22.4, what you obtain is the volume of H2 at standard conditions. It is not at 25 and 730 millimeters here. So the volume at STP is what you calculate from the standard equation, because you assume the standard equation to be 0 degrees and 1 atmosphere. Remember I said it's not going to have a sidebar that says this is at STP. The molecular equation as written is always at 0 degrees and 1 atmosphere assumed. So at volume at STP is 0.0038 mole of H2 gas times 22.4 liters per mole for any gas at STP. And we have 0.084 liters of the hydrogen gas at STP. Now, we need to convert that to 25 and 730. Okay, what volume at 25 degrees C and 700 millimeters does this represent out of that? All we did was work from moles through the standard 22.4, and now we're fixing to make an adjustment. What did the temperature do from standard? It went up, right? Yeah? Well, how does that affect gas if the temperature goes up? You get a bigger number, right? You get a bigger volume. Okay? Well, the pressure went down. Went to 730 from standard is 760, right? 760 for 1 atmosphere. So as the pressure goes down, what happens to volume? It's an inverse, Boyle's law. So decrease pressure, increase strength. So what you need to do is multiply this number, this, we can go milliliters, millimeters. This is 84 milliliters. You can adjust that one, because all I'm doing is multiplying by 1,000. Is 84 milliliters. Now I need a temperature adjustment and I need a pressure adjustment. That's what it says. We're adjusting for 25 degrees. Well, 25 degrees in Kelvin is 298 Kelvin. The standard temperature is 273 Kelvin. I need a ratio, watch this, I need a ratio between those two numbers that'll make that bigger number. I'll say it again. I need a ratio between 298 and 273 that'll make 84 a bigger number. Would that be 298 over 273 or 273 over 298? You don't know? It'll be the big number over the little number. That's right. 298 over 273. Now I've got a bigger number due to temperature effects. So you increase the temperature, you increase volume. Now if I'd have gone to minus 10 degrees, I would have had to make a smaller number, so I would use the temperature ratio that would make this standard number, this is at STP, go to a smaller number if I'd have used a smaller number. Now what about pressure? I got to get a bigger number because I went down in pressure. So the pressure is, pressure given is 730 millimeters. Well, the pressure standard, STP, is 760 millimeters. Well, I need a ratio of those two numbers here times that. That'll give me a bigger number. What do I use? Sure, 760 over 730. That will give you the volume of that gas produced at 25 and 730 millimeters of pressure. Whatever it comes out. 95.5 is what I get. That will back me up. And all I did was convert the given data to moles and first went to the standard and then adjusted the standard to non-standard by using ratios of the temperature values and ratio of the pressure values that would adjust the volume to the appropriate direction, increase it or decrease it, based on the law. Boyle's law is an inverse relationship and Charles' law is a direct relationship. Now that's not difficult to do. The issue you have to develop is working with multiple levels. But I give you a starting point, convert the data to moles, whatever it is, and then apply it to the standard equation.